All right, good morning. Let me just hook up my other device and we will get started. Okay, so I want to start by clearing up something on Monday's practice assignment. When we were dealing with integrals of the form f star dg dx from minus infinity to infinity, we could use integration by parts. And of course, this is dv and this is u. So we're going to get f star g evaluated at minus infinity and infinity minus the integral of g df star dx. And for some reason, a lot of people said that this second integral goes to 0. And their reason for saying that, I think, was that, I can write the f star more cleanly, that the derivative of f star is going to 0 at plus or minus infinity. And so their reasoning was that, well, if the integrand is 0, then the integral would be 0. If the integrand is 0 everywhere, then yes, indeed, the integral is 0. But look, I could draw some axes. All right, here's a function that is going to 0. All right, so here's f. It's going to 0 as we go out further along the x-axis. And likewise, df dx is going to 0 because, it's flattening out. So because this thing is flattening out towards infinity, you could say that the derivative is going to 0. You could say that the function is going to 0. Is the area under this curve 0? Da or niet? Yes or no?
No.
Definitely not 0. Yeah, this integral is definitely not 0. This area is non-zero. Because the integral is not just the integrand everywhere. The integral is the antiderivative evaluated out here at plus infinity and out here at minus infinity. And it turns out that the antiderivative out here, if we were able to do the antiderivative exactly, would be non-zero. It would be a positive, would probably be non-zero. Technically, it could be 0, and then the antiderivative down here could be a negative number. We would get that 0 minus a negative number is some positive area under the curve. Or maybe it would be negative out here. Maybe the antiderivative would be negative out here and be even more negative out there. And so a small negative number minus a large negative number becomes a small negative number plus a large positive number, since minus the negative is positive. On the other hand, in this thing here, I only care about the values of f and g at plus infinity and minus infinity. So that goes to 0. Any questions on that? Going once, going twice. All right. That takes us to the fact that when we do integration by parts for the product of one function, or the complex conjugate of one function and the derivative of the other, we get minus the integral of the opposite pairing. which means that if we replace the derivative with I times the derivative, right, then what we've got is on the left side, the inner product of f with I dg dx. And on the right side, we've got the inner product of minus I dg df star dx with g, which would be the complex conjugate of, and really I should be writing just f there because it's always the function in the first position that gets complex conjugated. So whenever I have that, sorry, let's just back up. This is the inner product. This integral up here is the inner product of f with I dg dx. Then this looks like the inner product of g star minus I df star dx. So you could say, but we don't have a g star in there. We have a g. Well, yeah, but the thing in the first position gets conjugated, and the conjugate of the conjugate is whatever your original complex variable was. Right? Which is, all of this is the complex conjugate of g I df dx. So the whole idea of a Hermitian operator is that you could do the inner product in either order. And if you do the inner product in the reverse order, you're complex conjugating it. So when I went from this inner product to this inner product, the only thing that changed was a complex conjugate reflected in that minus I. It gets complicated. So let's back up and do a simpler case. Let's say that f and g are real functions. All these things are easier to do if you first do it with just real functions and then fill in some complex conjugates at the end. Everything gets really confusing if you try to do it complex from the beginning. The inner product of f with I dg dx all right, and this is, we're assuming these are real functions, so we don't have to complex conjugate the functions. And we worked out via integration by parts that that's minus I times this. So I'm going to call I d by dx, I'm going to call that P, because it's similar to the momentum operator in quantum mechanics, except that technically I should be calling it px. If you want to, I'll make it minus I everywhere so we can be as consistent as possible with what you're doing in quantum mechanics next year. In quantum mechanics, the x component of momentum turns out to be minus I times the derivative of your wave function. Technically, I should be writing it as h bar over I d by dx. But in grown-up units, h bar is 1. H bar is always either 0 or 1. It's 1 doing quantum mechanics in grown-up units, it's 0 in classical mechanics. And it's h bar in experimentalist units. And yes, experimentalists are grown-ups. They're just grown-ups who have certain unique needs when it comes to numbers. But theorists try to make all of their numbers 1, 0, -1, 2, pi, I, or E. If a theorist can get through the day with 1, -1, 0, 2, pi, I, and E, they call it a good day. All right? So here we've got f minus I dg dx. And over here we've got the inner product of g times minus yeah, I'll do it that way. Conjugated. Because on the right side, we've got the inner product of g with the derivative of f. And you're saying, no, we don't, because we've got this plus I instead of minus I. Well, then we conjugate it at the end. Anyway, that's what it means for operators to be Hermitian. It means that when you swap an order, all you're doing is taking a complex conjugate. It's just like when we said that this matrix is Hermitian, because if we swap the order of things or transpose the matrix, we get a complex conjugate. I replace I with minus I, right? So this operator obeys the same basic structure as a Hermitian matrix. Swap in order, complex conjugated, and everything's the same. And we proved that these kinds of operators have real eigenvalues and eigenvectors corresponding to different eigenvalues give you, the eigenvectors corresponding to different eigenvalues are orthogonal. And so what I wanted you to see on the assignment you turned in today was that if I have something like d by dx of e to the minus x squared dy dx equals, I think it was minus 2 nu e to the minus x squared y, this is an eigenvalue problem. And this is a Hermitian operator because this is px e to the minus x squared px. It's just a product of 3 Hermitian operators in a symmetric order. All right, 3 Hermitian operators in a symmetric order. And technically there should be a minus sign there if I'm going to call it px, because each p gives us a factor of minus I, and minus I times minus I is minus 1. But we've got 3 Hermitian operators arranged symmetrically. And so anything that's an eigenvector or an eigenfunction of this operator, this product of 3 operators, must be orthogonal to other eigenfunctions that have different eigenvalues, that have different values of nu. And this e to the minus x squared is the row. Because if I took y I d by dx e to the minus x squared dyj dx, that's got to be yi minus yi, all right, minus 2 nu j yi yj e to the minus x squared. And it's nu j, it's the eigenvalue corresponds to eigenfunction j because eigenfunction j is the thing that we acted on. And we know that if we integrate both sides, because of all the things that we've done repeatedly with integration by parts, we are going to get the same function back, maybe with a minus sign. We're going to get, we're going to get this. We're going to get, if I do these limits from minus infinity to infinity, all right? We're going to get this, which doesn't depend on the order I and j. I can swap I and j, and I would get the same thing. And I could swap I and j, and I would get the same thing, except that if I swap I and j, this thing changes. That was the argument that I referenced on Monday. And so what I wanted you to see on the homework, based on the argument that we had made before in the previous weeks, and then again referenced on Monday, if I take the inner product of some eigenfunction with this operator acting on some other eigenfunction, I get two integrals that don't depend on which one is I and which one is j, yet they've got this prefactor of an eigenvalue that does have an index on it, okay? And then if I swap I and j, this integral shouldn't change, this integral shouldn't change, yet this number out front does change. The only way that changing the number out front changes absolutely nothing is if we either do congressional math on budgets or we have zero. So we've got some changing number multiplied by zero, and absolutely anything multiplied by zero is zero. So this inner product must be zero. That's what I wanted you to see. And this is the weight function, all right? This thing that shows up on the right-hand side that goes into that integral, that's the weight function. Now, I've been doing this somewhat arbitrarily, invoking various differential equations, but on Friday's practice, sorry, not practice, on Friday's follow-up assignment, you're going to do it for two different forms of the wave equation, because it turns out that the wave equation often gets written in two different forms. One of those forms is, well, you know what, let's just do Maxwell's equations, right? Let's just go directly to Maxwell's equations. We're at the end of the semester. I'm not going to give you any new material that I'll test you on. I'm just giving you applications of what we already did to set up the one follow-up. Maxwell's equations. Del cross E equals minus partial B partial T. Del cross now I have to be very, very careful with something. Mu H, curl of H. Del cross B over mu, where mu is the magnetic permeability of the material. And I think I'll rewrite this as because B equals mu H, and I'll rewrite this as del cross H. All right, these are Maxwell's equations written out in quasi-grown-up units. I say quasi-grown-up because on the one hand, there are no factors of C, 4 pi, mu naught, or epsilon naught, but there are material parameters. And the snobbiest of theorists would say we only deal with fundamental fields in space, but we're going to deal with materials here. So we're kind of grubby, practical grown-ups. We're the grown-ups who had to get a job here rather than the grown-ups who are doing pure aristocratic physics. Aristocratic physics. Yes. So I could rewrite this. Let's say that J equals rho equals 0. We're in space that might have materials but has no free charges. All of the charges that we're going to worry about are already in materials. And so the motion of those charges is captured in the properties of the materials. Then I could rewrite this as del cross E equals minus mu partial H partial T. And del 1 over epsilon del cross H equals partial E partial T. Then what I'm going to do is I'm going to take the time derivative of both sides of this. So I'm going to take another time derivative. And I'm going to get that partial squared or minus mu times partial squared H partial T squared equals del cross partial E partial T. And I'd be saying, why isn't it the time derivative of the curl? Because when you're taking derivatives with respect to two independent variables, we can swap the order. We can either take a time derivative and then a space derivative, or a space derivative and then a time derivative. Well, let's see, we already know what partial E partial T is. It's that. Okay, so the curl of that del cross partial E partial T is del cross 1 over epsilon del cross H, and that is equal to minus mu partial squared H partial T squared. Or if I put it all together, I get 1 over mu del cross 1 over epsilon del cross H.
Professor?
Minus partial squared H partial T squared.
The reason why you said we could take a time derivative first and then a spatial derivative first, or vice versa,
Yeah.
is that because of the uncertainty principle, or is it because the operator is Hermitian?
Neither. It's because these two operators commute because space and time are independent variables.
Okay.
Doesn't matter which one we change first. Okay, why am I harping on this? And why am I harping on this today in this context? Because one of the first things I was assigned to read in graduate school was a book on photonic crystals, photonic band gap materials, where they open by writing Maxwell's equations in this way. And then they made the following observation. They made the observation that for all of the materials that they were going to care about, mu was 1. Often, but not always. And if mu is 1, then we've just got this. And we've got this symmetric product of, I'm going to write it as minus I curl crossed with 1 over epsilon. This is a function of x, y, and z, because epsilon does depend on the kind of material. Epsilon can be very, very different from 1, because the refractive index of a material is very different from 1. And people who work on photonic crystals are interested in things like, well, what happens if I, say, assemble a Lincoln log structure of materials? And then I keep on alternating stacks of materials, and I propagate light through that Lincoln log structure. And it turns out that light does very, very unusual things in materials like that. And so we need to solve Maxwell's equations in a system where epsilon is, say, 10 in some parts because it's silicon, and 1 in other parts because it's air. So we have the symmetric product of 3 operators, minus I curl, and I'm writing it as minus I times curl rather than curl so that it's Hermitian, and another minus I curl, and in between them, this function of x, y, and z, a symmetric product of Hermitian operators. Hermitian operators are symmetric, so a symmetric product of symmetric operators is symmetric. All right. And I got rid of the minus sign on the right because I've got a minus I times minus I here. That way I've got a symmetric product of symmetric operators, which is symmetric, it's Hermitian. And the authors said, okay, if we write Maxwell's equations in this way, then we've got a Hermitian operator on the left, and there are a whole bunch of theorems that we could invoke for Hermitian operators. So that's why they wrote Maxwell's equations in this way. And then the rest of the book proceeded to deal with how you solve them that way. And you can get that book online nowadays. They've got a free PDF on the author's website. Joannopoulos et al. If you just Google for Joannopoulos, and I can never remember when you're transliterating Greek names into English, whether it's 2 N's and 1 P or 1 N and 2 P's, but if you Google for Joannopoulos, any reasonable spelling thereof, Joannopoulos et al. Photonic Crystals book, you will find the author's website with a free PDF of it. Okay. And they contrasted this with the way that we had usually been taught to write down Maxwell's equations, which was to do, or to turn Maxwell's equations into the wave equation, which was to do del cross E, starting up here. And that would give you minus d by dt of the curl of mu h, and the curl of h is j, which we're assuming to be 0, plus epsilon times the derivative of E. And so when all the dust was settled, you would have to then take into account the fact that sometimes mu does change with position, but whatever, we'll ignore that today. Mu is 1. And so we get minus epsilon partial squared E partial t squared. Or I could write that as 1 over epsilon minus I curl cross minus I curl okay, and they observed in the beginning of the book that this is Hermitian, this is Hermitian, and this is Hermitian, but it's not a symmetric product. And because it's not a symmetric product, If you take the Hermitian conjugate and you swap orders, you don't get the same operator back. All right, you don't get the same thing back. And so because you don't get the same thing back, they were not going to solve Maxwell's equations that way. They were not going to solve for E, even though E, the electric field, is what we're more used to because it exerts an electric force on charges, which is a non-relativistic force, whereas magnetic fields are inherently relativistic. And it's actually harder. It's not that much harder, but it's a little bit messier to do the quantum mechanics of electrons interact or atoms interacting with EM waves if you do everything with magnetic fields. So it's not a symmetric product, not Hermitian. Now I'm not going to have you on the follow-up assignment do 3D derivatives of vector fields. I'm going to have you do something much simpler. I'm going to have you compare this equation or something like that versus this one is clearly Hermitian. And because it's clearly Hermitian, we can make very clean statements about the orthogonality of fields corresponding to different omega values. This one is not Hermitian. But with just the tiniest amount of work, you can turn it into something that looks like the kind of equations that are set up in the textbook chapter that look kind of like d by dx, p of x, d by dx, y equals lambda rho of x, y. And then you can come up with an orthogonality relationship for that, right? So I'm giving you simplified versions of the wave equations that I encountered in my first big reading assignment in grad school to see if you could come up with the orthogonality relations for those functions. Any questions? All right. Then I want to go a little bit farther with the analogy between vectors and functions, because that analogy will enable us to derive the uncertainty principle. We alluded to it. We found repeatedly when we took Fourier transforms that if you had a function that was really wide as a function of x, if you have f of x here, then a of k would be very narrow. Whereas if f of x was narrow, then a of k would be very wide. We observed that time and time again. Now I want to prove that that has to be true. And I want to start it by proving an inequality, which has the fancy name Koshi-Schwartz inequality and doesn't look like anything from geometry, but it actually is. Koshi-Schwartz inequality says that the inner product of two functions, absolute values squared, is less than or equal to the inner product of one function with itself times another function with itself. Well, let's think about what these two sides mean. This is basically a squared dot product because the inner product of two functions is just the higher dimensional generalization of the dot product of two vectors. And here's a squared length. And here's another squared length. Well, if we had two vectors, A dot B, we know that that's the length of A times the length of B times the cosine of the angle between them. And if I take the absolute value of that, we got the absolute value of cosine theta there, which is between 0 and 1. So it looks to me like the Cauchy-Schwartz inequality is basically just taking a fact of dot products and generalizing it to higher dimensional vector spaces. Okay? And now we're going to prove it. We're going to start with this statement. Two functions f and g and some constant lambda, and the squared length of f minus lambda g is greater than or equal to 0, which is true no matter what, because any vector's length must be non-negative. Any vector's squared length must likewise be non-negative. So the length of f minus lambda g is clearly greater than or equal to 0. So I could rewrite this. Any squared length is an inner product. So I could rewrite this as f minus lambda g inner product with f minus lambda g. And now I've just made this into a statement about inner products, which gives us some hope of maybe relating it to this inequality up here. That's going to be inner product of f with itself minus the inner product of f with lambda g minus the inner product of lambda g with f plus, well, I'll write it out explicitly, lambda g inner product lambda g. Or inner product of f with itself minus lambda inner product of f with g minus lambda complex conjugate inner product of f with g complex conjugate, because I'm just swapping around some orders here, plus absolute value of lambda squared inner product of g with itself. Any questions? All right, so far I haven't made any real assumptions here other than lengths are greater than or equal to 0. Lengths would be equal to 0 if the function is 0. Now let's pick a very particular value of lambda. We're going to say that lambda just happens to be the inner product of g with f over the inner product of g with itself. And the only reason I can give you for picking this is that it works, okay? It's going to give us a statement that we want. So we're going to, and by the way, all of this is greater than or equal to 0. So now we've got inner product of f with itself minus inner product of g with f, inner product of f with g over the inner product of g with itself. By the way, you notice how in this notation, we get something kind of symmetric in the middle of this sandwich here. That turns out to matter in quantum mechanics. That turns out to matter in something called Dirac notation. We're using something that's almost but not quite Dirac notation. You're going to see things set up this way. these brackets, this bracket notation in quantum mechanics a lot. All right, minus lambda star. Well, let's see here. Lambda star, if lambda was inner product of G with F, lambda star will be inner product of F with G. And then inner product of F with G star. I'll write that as G with F. Again, over inner product of G with itself, plus lambda squared, absolute value of lambda squared. That'll be GF FG GG over GG squared, because we're squaring lambda and GG is on the bottom. Well, it looks to me, and all of this is greater than or equal to 0. Looks to me like we have 3 terms that are, if not exactly the same, at least very similar. Actually, they are the same thing, except with different signs. GFFG, these 2 things are the complex conjugates of each other. These 2 are also the complex conjugates of each other. These are also the complex conjugates of each other. So in each case, we've got, other than the first term, we got minus, minus, plus. We got FF minus and then we've got GG on the bottom here, GG on the bottoms here, and GG over GG squared here, which is 1 over GG. And I've got FF minus FG squared over GG. If I add this to both sides, if I take this thing and add it to both sides, I've got FF greater than or equal to FG squared over GG, or FFGG greater than or equal to FG squared. Any questions? All I've done so far is basically prove that this inner product, which is a generalized dot product, obeys a simple property of the generalized dot product. Now I get to use it to prove the uncertainty principle. Which is just a property of Fourier transforms. It's not quantum weirdness. There's absolutely nothing quantum mechanically weird about this. The thing that's weird about quantum mechanics is that momentum is essentially the Fourier transform of the wave function, okay? That's what's weird about matter. What's weird about matter is the particles behave like waves and the momentum is related to the Fourier transform of the wave. That's what's weird about quantum mechanics. But the fact that Fourier transforms obey an uncertainty principle, that's as weird as the sun rising in the east and setting in the west. It's just a fact, okay? And it's a fact with an underlying explanation. So here's the uncertainty principle. Let's start by assuming that a function has the property FF equals 1. That just means that the integral from minus infinity to infinity of the absolute value of f squared dx is equal to 1. And if it were something other than 1, Well, then we could just multiply or divide by a constant and redefine f appropriately, and then it would be equal to 1. And the main reason to do this, aside from making 1 or 2 steps easier later on, is that then we can interpret absolute value of f squared as being like a probability distribution. In quantum mechanics, you're dealing with probability distributions all the time. Let's also assume that the integral from minus infinity to infinity assume 1, assume 2, that the absolute value of f squared x dx equals 0. Okay. Now, what that means is that we're not assuming that f squared is symmetric. Certainly, if f squared is symmetric, this will be true. If f squared is an even function, if this is the absolute value of f squared, then the absolute value of of f squared x would be that, and clearly the integral is 0. But we could also have asymmetric functions. We could have a function that's asymmetric and is big on the left. Actually, has a very high peak on the left, and then drops but decays slowly. And that would be easier if I had made this here. I'll draw it a little bit better. All right, so there's my axis, and then it's going to, I've got to show at least a little bit of decay on this side. Whoa. Now I'll do it more like that. Very gradual decay. If we set this up just right, we could still get that the integral of f squared x is 0. And if I set it up a little bit wrong, well, then I could just shift my axis so that now it works. Or shift my axis again. I could set my axis wherever I need it to be so that this works. All right, you can say, wait, how can I just shift my axis? Well, I can shift my axis really easily. And the beautiful thing is, what do we know about shifting something back and forth along the x-axis? What does that do to the Fourier transform?
It modulates it.
Yeah, I could modulate it. We could shift f of x if needed. A of k will get multiplied by e to the I k delta x, or delta x is however much we shifted it. Okay, so we multiply a of k by this phase factor, but what happens to absolute value of a of k squared?
You just get a power spectrum?
Well, that's the definition of a of k squared, but my question is, how does the power spectrum change if I multiply a of k by e to the I k delta x?
If you're using the complex conjugate definition, it wouldn't, right?
Yeah, we're defining the absolute value squared as a multiplied by its complex conjugate. So what happens?
Nothing.
Absolutely nothing. Okay, and so although we're changing the Fourier transform, we're not changing the absolute value squared of the Fourier transform. So then let's make one final assumption, which is that the integral from minus infinity to infinity of absolute value of a of k squared k dk, that is also equal to 0. And you can say, well, that's not guaranteed. Well, no, it's not. But I could always, if necessary, again, shift my Fourier transform. You know, here's a Fourier transform that might have that property. It might be, you know, even though it's asymmetric, it's got a long tail here, which is going to give you a lot of area here. And it's got a spike here and then a smaller tail. So these two things might kind of cancel out, and we might still get that k a squared of k is 0. It's possible, it's not guaranteed. And if it didn't happen, well, then I just shift to a new axis here or wherever it needs to be. And so if I shift, I can always shift my Fourier transform back and forth. Now shifting my FT, shifting it to a of k minus delta k replaces f of x with e to the I delta k x f of x. But what is, you're thinking, okay, well, that's a problem. We're changing f of x. We just made these assumptions about f of x. But our assumptions were about the absolute value squared. And if I multiply f of x by e to the I x delta k, what exactly happens to absolute value of f of x squared? Don't overthink it.
Nothing again.
Absolutely nothing. So what you need to take away is that I'm making some assumptions that will make the subsequent steps easier, but they don't really change any of the probability distributions that we're dealing with. We can always make changes to these functions that don't really change the key features of the probability distributions. Okay, well, the uncertainty principle says that the variance of x times the variance of k is greater than or equal to some bound that we're going to calculate. And the variance of anything is equal to the variance of x is equal to the average of x squared minus the square of the average. It's the average of the square minus the square of the average. All right. And the average of x squared is the integral of absolute value of f squared times x squared dx. And the average of x is the integral but we just assumed that this is 0. And likewise, the variance of k is the average of the square of k minus the square of the average of k. And we assume this one is 0. So what we're left with is we're left with this. We are left with absolute value. I can rewrite this. I'm going to write it as something different. I'm going to write this as the integral from minus infinity to infinity of x f star f x dx, and integral from minus infinity to, oh, and that shouldn't be f, that should be a. Okay. Well, this looks like the inner product of xf with xf. And this looks like the inner product of ka with ka. All right. So you've got the inner products of two functions with themselves. And so we're trying to prove that xf, inner product xf, is greater than or equal to, sorry, ka is greater than or equal to some bound. So I've got two different functions. And I need to prove that their inner products, that the products of their inner products with themselves are greater than the bound. Well, lo and behold, we just happen to have something like that up here, the Cauchy-Schwartz inequality, which says if I've got a function f, well, now it's not f, it's xf, but you know, that which we call xf would by any other name still obey the Cauchy-Schwartz inequality. And g, except we're calling it ka, but that which we call g would by any other name still obey the Cauchy-Schwartz inequality, that's got to be greater than or equal to the square of the inner product of f with g. So I can conclude that the variance of x times the variance of k is greater than or equal to the inner product of xf with ka absolute value squared. Any questions on how I got there? All right. Well, we can also conclude that this whole thing here must be equal to the real part squared of xfka plus the imaginary part of xfka, whole thing squared, because you know xf, inner product of xf with ka could be complex. It's going to have a real part, it's going to have an imaginary part. And it turns out when we turn the crank on the algebra that is a whole lot easier to deal with, that the imaginary part is easier to deal with. All right. The final thing we know is that Ka is the Fourier transform of xf. Sorry, it's the Fourier transform of minus I df dx. All right. So we could just deal with that, because we know that if I want to take the inner product of two functions, any two functions, I can either integrate over all x values. I could take these two functions, integrate it over x, or I could take the Fourier transforms of them and integrate over k, all right? I get to choose which space I'm going to integrate in. That's from Parsifal's theorem. Integral from minus infinity to infinity of, I'm not going to use f and g. I'm going to say psi star phi, these are two functions, dx equals the integral from minus infinity to infinity of a psi star, a phi star, where these are the Fourier transforms. Oh, and that last one, the second one shouldn't have been starred, my bad. dk. So now I've got finally, after invoking a bunch of theorems, I've got that this inner product is the integral of x times a complex conjugate of a function times the derivative of a function. For this, integration by parts was invented, okay? This is why we need integration by parts. We've been doing integration by parts for weeks for proving all of our different theorems. We are tanned, rested, and ready to do some integration by parts. We are primed for this, all right? So we are going to get, if I call this u and I call this dv, then du is going to be x df star dx plus f star, whole thing multiplied by dx, because the derivative of x times f star, we have to use the product rule. So I'm going to get x f star times minus I f evaluated from 0 to infinity. Sorry, minus infinity to infinity. And we don't know exactly what f is, but we know that if f squared is integrable, if we can integrate f squared from minus infinity to infinity, as we assumed up here, absolute value of f squared must decay faster than 1 over x. Right? If absolute value of f squared doesn't decay faster than 1 over x, then we couldn't do the integral. All right, that's just freshman calculus right there. These integrals from minus infinity to infinity only work if your function decays very rapidly as you go to plus or minus infinity. So this product must be decaying more rapidly than 1 over x, which means that, yeah, we're multiplying by x, which is going to infinity, but f star f is going to 0 even faster. So x times f star f must be 0. And then we're left with plus I times integral from minus infinity to infinity of v du, okay? So we're gonna have f star plus xf df star dx, whole thing multiplied by dx. One of these is easy. We assume that it's equal to 1. We assume that at the very beginning. The other one, okay, we've got a mess on our hands. Except I said up here, you know what? What if we know that we could break this into something involving a real part and something involving an imaginary part. If we break this up like that, that must be bigger than or equal to the imaginary part squared. All right, the thing that we're looking for must be bigger than the square of the imaginary part of that inner product. Because it's greater than or equal to the whole inner product squared. If it's greater than or equal to something squared, and that something has both a real and an imaginary part, well, it's got to be greater. If it's greater than the whole thing, it's got to be greater than a piece of it too. All right. And the imaginary part of XF KA is equal to XF KA minus KA XF whole thing divided by 2I. All right. So I've got XF KA here. We know that XF KA equals I plus I integral from minus infinity to infinity XF df star dx. And if I were to subtract off KAXF, I would be subtracting off, well, let's see here. Hey, I would be subtracting off the integral I originally had, right? The complex conjugate of the integral I originally had. The complex conjugate of the integral that I originally had, we'd replace a minus I here with an I, an F star with an F, and the derivative of F with the derivative of F star. So we would be subtracting off I integral of X F df star dx. And then we would be dividing by 2I because we'd be subtracting off the complex conjugate of this. And when we subtract off the complex conjugate of this, we're subtracting this term here, which lo and behold exactly cancels that integral. The integral tweeted something terrible and got canceled. And so we are left with that the imaginary part of that inner product is 1/2. And the square of that imaginary part is 1/4. So the variance of x times the variance of k is greater than or equal to 1/4. The variance is a measure of width. It's a measure of just how wide that peak is in f of x. And the variance of k is a measure of just how high that peak is in a of k. The variance is the squared width of f of x. Here we've got squared width of a of k. The squared width of one multiplied by the squared width of the other is greater than or equal to 1/4. Any questions? Okay, so we got this from the Cauchy-Schwartz inequality. And the Cauchy-Schwartz inequality is an inequality about dot products. It's an inequality, it's basically a generalization to functions of just a basic fact about the dot product of two vectors. So we've kind of come full circle. I promised you at the beginning of the semester that we would talk about how to take functions apart into little pieces. So we did Taylor series. We did Fourier series. We did Fourier transforms. Then we talked about the orthogonality of Legendre polynomials and how we could break certain functions into Legendre polynomials like you did on assignment. We talked about the orthogonality of Bessel functions and how we could break functions into Bessel functions, which we talked about last week, series of Bessel functions. We showed that these Bessel functions and Legendre polynomials are examples of things that solve pieces of the wave equation, and solutions to the wave equation can be built out of pieces. And then we went back to that idea of functions as vectors, proved an inequality that looks a lot like dot products. And then, yeah, we followed some algebraic gymnastics. I know it's a lot to chew on, but by following those algebraic gymnastics, we proved rigorously something that you saw qualitatively earlier in the semester, when you would take a function and play with some parameter and say, hey, look, as I change this variable, f of x gets wider, or f of x gets narrower. And then when I change that same variable, if it made f of x wider, it makes the Fourier transform narrower. And if it made f of x narrower, it makes the Fourier transform wider. So finally, we talked about orthogonality of solutions to general differential equations, and I showed you how that is related to some basic facts about representing the wave equation as a symmetric product of Hermitian or symmetric operators. And your final assignment for the semester has you, among other things, figure out what would the orthogonality relations for different solutions to the wave equation be. So we've done everything I promised. All that's left now is a final exam. On Friday, during the recitation time period, I'm not going to give you a new activity. I'm just going to take questions. So come prepared with questions from all of the different problem sets and midterms. The structure of the final exam will be that you'll have 4 short questions, 4 long questions. In each group of 4, you can assume 1 from each midterm and 1 from things after the midterm. And so you should come with questions from the midterms and questions from the last few problem sets. And I'll just take questions for as long as you want on Friday. Then on Monday, I'm going to make the final exam available most of the day. For the handful of you who have 3 exams on one day, talk to me and we'll make arrangements for Tuesday. So far, I think only 2 people have talked to me about arrangements for Tuesday. I've written this exam to be as long as the midterms, but I'm allowing you twice as much time as I gave for the midterms to account for the fact that different people have finals at different times. There are a few people who, for various reasons, are allowed extra time, but because I'm already making the time double while making the test the same length as before, I think that satisfies all of that. I don't want to have to adjudicate a whole bunch of different exceptions. I just want to give enough time so everyone can do what needs to be done. Now we're at 11:15, so you're free to go. I'll take questions if you want to stick around afterwards. Otherwise, I'll see you Friday.
Thank you, Dr. Small.
You're welcome.
Thank you, Professor.
Thanks, Dr. Small. See you Friday.
See you Friday.
Hey, Dr. Small,
Yeah.
do you think you can quickly go over 4B from the last homework set?
Sure. And I already disconnected my device, but I can at least talk about it. All right, let me look at 4B. Hermite polynomials. What is the orthogonality relationship? Okay, the orthogonality relationship is going to be integral of hi hj times e to the minus x squared is equal to 0 if I and j are different.
Yeah, that's what I actually wrote for my final answer, but I feel like that wasn't like, that was just like the general equation. I didn't know
That's all you
how.
need to say. You need to say that based on these things, we can immediately conclude that, you know, if our
Information.
on the right-hand side is e to the minus x squared, then it's yi, yj, e to the minus x squared. That whole integral is 0.
Oh, cool. Okay. Cool. Okay, thank you. Because yeah, I found like I remember you directed me to chapter 17. And I found like some graph that said like you can say that this is Hermitian if, you know, e to the minus x squared is rho and blah blah blah. But thank you.
Mhm.
Professor, I want to expand on that. I believe on the problem set you wrote something that has to relate to H, and you know this is one of the scenarios where like it's either
H is just another name for a solution to the Hermite equation.
Oh, okay. So I thought it was the Hankel function because we were working with Hankel functions earlier, but
No, Hankel functions have a superscript.
Oh, okay. Okay. So I should, yeah, okay. That makes more sense. Okay. Thank you, Professor.
You're welcome.